In this session, let us look into the next part of probability, that is nothing but independent events. Now, I'll just give you a very simple example about independent events. Let us assume that I'm going to toss a coin twice. Now, if I'm going to toss a coin once, I'm going to get a head. And in the next toss, if I'm going to toss it for the second time, whatever the result I have obtained in the first toss, it will never affect the second toss. If it is head, based on that, I cannot say it can be head or tail, isn't it? Based on this head, I cannot say the next one can be head or next one can be tail. It is completely independent. This type of problem is nothing but independent events. Similarly, when you roll a dice once, you might get any of 1, 2, 3, 4, 5, 6. Whatever the number you're going to get, it is not going to affect the second throw, isn't it? This is nothing but independent events. Now we are going to understand the independent events. Before this, we have already seen multiplication theorem on probability, isn't it? Which was a continuation of conditional probability. From conditional probability, we got multiplication theorem, and the next condition, if you apply one new condition, that is an independent event, to the multiplication probability, we are going to get a new formula, that is a formula for independent event. Now let's try looking into this. As we have already seen in the previous session about the multiplication theorem, it says that probability of any x intersection y is given by probability of the first event times the probability of the second event, provided the first event has already happened. Right? This is the condition. Now, if you are going to look into the independent condition, it says that if you are going to roll a dice once, the second throw will not get affected by the first one. So it means that for the second probability, if the first one is going to happen or not happen, it is not at all going to affect. So it means that I can say probability of the first event times, this can be written as the probability of the second event when it is independent. This is very important, when it is independent. So what is the formula for independent probability? That is nothing but probability of one and the other is given by the probability of the one times the probability of the other. That's what we are going to see in independent event. So it has been completely derived from the multiplication theorem. Just remember this formula about independent probability. It says probability of one and the other is given as probability of one times the probability of the other. Now, if they have given three events, it should be probability of one times the probability of second times the probability of third. So this is what you need to understand. So now, if they're going to give any question and if they're going to ask you to check whether they are independent or not, or check for the independency, you have to just check whether these two are exactly matching or not. If it is matching, then they are independent. If they're not matching, then they are not independent. That's as simple as that. Okay. Now let's look into a few of the points here. Extension of multiplication theorem for independent event. Now I have already told you about the multiplication theorem. Independent event is one extra condition on multiplication theorem. Now, if you're going to apply for two events or three events or any number of events, it is not going to affect. So overall, you can say here probability of x1 intersection x2 intersection up to xn can be given as the product of the probability of all the items taken individually. So this is about your independent events. Next, let's try understanding few of the important points here. Probability of happening none of them. Now we are going to check out probability of none of them is going to happen. It means first one is not going to happen and second one is also not going to happen. Third one is also not going to happen. It means anything is not going to happen. So can I say and? It means nothing is going to happen. So you're going to take first one not happening. That's why you have taken X bar. Second one not happening. Third one not happening. So this intersection, you can take it as a product of individual events only when they are independent. Probability of X1 not happening is given by 1 minus P1. Probability of x2 not happening, 1 minus p2. Similarly, it goes on. Next, probability of happening at least one of them. So now at least one of them is a huge event. I can say one is happening, 2 is going to happen, 3 is going to happen, 4 is going to happen, up to n is going to happen. It's a huge collection of events. In order to solve this, what we can do is we can take a negation of it. That is nothing but 1 minus nothing is happening. If you take 1 minus nothing is happening, it gives you at least 1 is happening. So we have already taken out nothing is happening here. So you just take it as 1 minus the previous value. That is nothing but 1 minus P1 times 1 minus P2 times 1 minus P3. It goes on. Next, probability of happening of first event and not happening the remaining. Now if they're going to look into this, we have already seen that probability of not happening. First one is not happening, you just take negation. Second one not happening, negation. Third one not happening, negation. So it means if they're going to give in this condition saying that it is independent event, you can take it directly. They have given here first event happening and the remaining not happening. You just take probability of x1 times probability of x2 not happening, x3 not happening, xn not happening. So we can take it as P1 times 1 minus P2 times 1 minus P3 times up to 1 minus Pn. So this is how you can easily apply the probabilities for an independent event just by taking the multiplication in consideration. Let's try taking out a few examples here. First example goes like this. Let A and B be the events with probability of A equals to 3 over 5, probability of B is 3 over 10, and probability of A intersection B is 1 over 5. Check whether A and B are independent or not. In order to satisfy the independent condition, I need to prove probability of A intersection B is equals to probability of A times probability of B. Now if you're going to look here, probability of A is given by 3 over 5, B is given by 3 over 10. You just multiply this, you're going to get it as 9 over 50. And they have already given probability of A intersection B, which is going to be 1 over 5. You can check that 9 over 50 is not equals to 1 over 5. So they are not independent. Similarly, let's look into the second example. An impartial die. Impartial die means you are going to get the random results and a fair coin are tossed. Let head appears on the coin A and 3 appears on a die B. Represent the respective events. Verify whether event A and B are independent of one another. Of course, A and B are independent, but we need to still prove it. So now if a fair coin and an unbiased die are tossed, the sample space can be given as, so first sample space for a die. If you're going to roll a die, you're going to get it as 1, 2, 3, 4, 5 and 6. And if you're going to roll or if you're going to flip a coin, you're going to get it as head or tail. Now if you're going to roll a die and if you're going to toss a coin, you're going to get a combination of this, that is H1 2 3 4 5 6, T1 2 3 4 5 6. This will be our sample space. Now they have said that condition 1, head appears on a coin. So now if head appears on a coin, I can say we are going to get 1, 2, 3, 4, 5, 6 possibilities out of 12, which is nothing but 1 over 2. Now second, event B says 3 on a die. Now if I want to get 3 on a die, I can say we have got 2 possibilities where I can take it as 2 over 12, which is nothing but 1 over 6. Now, if I'm going to take out the intersection of A and B, I have to look here that H comma 3 is the one which is in common. So I can take it as 1 over out of the total 12 which falls in both. Now I need to check with both. So first one is P of A and P of B. 1 over 2 times 1 over 6, which is going to be 1 over 12, which is exactly matching with probability of A intersection B. So I can say that A and B are independent events. This we were knowing it earlier itself because rolling a die and tossing a coin both are 2 different events, but still we need to prove it. This is the proof here by taking out mathematically. Now let's try going on with a few more questions here. Now let's look into first question. When a coin is tossed, what is the probability of receiving 5 heads in a row? When a coin is tossed, I've already told it is independent event because one event one tossing is not depending on the other tossing. So now they're asking us about the probability of receiving 5 heads, all 5 heads in a row. So it means that probability of first one is head times probability of second is also head times probability of third is also head times probability of fourth is head and probability of fifth is also head. So now if I'm going to take it as probability of getting head, we are going to get head or tail as a sample space. Getting head in one tossing is 50%, which is 1/2 times 1/2 for this times 1/2 for this times 1/2 times 1/2. I can take it as 2 to the power 5, which is going to be 1/32 as our final answer. This was a very simple question. Now let's try going on with a few more questions. Question number 2. A bag holds 4 pairs of socks, pink, red, blue and yellow. Let me draw a bag here. So which has pink, red, blue and yellow. Without noticing, you reach into the bag and select a pair of socks. After changing this out, you select a different pair of socks. What is the probability that you will select the pink socks on both occasions? So now you have to select pink socks in both occasions. And they have told that after changing this out, it means you're going to pick one pair of socks and you're going to put it back. So now we are going to find out the total probability as first one is pink and second one is also pink. Since you are going to keep it back, so the event is not going to affect the another event, so it is independent, so I can just take it as a product. Probability of selecting pink pair of socks out of 4, if you're going to select one which is pink, so you're going to get 1/4 times the other one which is also 1/4, so I can say the answer is going to be 1/16. I hope it is clear. Then let's move on with question number 3. In this question, they have said that S and R are 2 distinct events. So since S and R are 2 distinct, I can say they are going to be independent. And if probability of S is 0.3 and probability that S union R is 0.5, then we have to find out the probability that you get S provided R is already done minus probability of R provided that S is already done. So now if you're going to look into this, since they are independent events, I can say probability of S given R can be directly taken as probability of S, and probability of R given S can be taken as probability of R directly. Now they are asking us to find out this value, probability of S minus probability of R. In order to find this out, I need to find out the probability of R first. We have already seen 3 conditions earlier. Probability of S union R, it means that at least one is going to happen. I can take it as 1 minus probability of nothing is going to happen. So I can take it as probability of S bar times probability of R dash, R bar. So I can take it as 1 minus probability of S bar is going to be 0.7. Probability of R dash is not known. I'll write it as it is. And probability of S union R is already known, which is going to be 0.5. So I can take it on the other side. I can write it as 0.7 times of probability of R dash is equals to 1 minus 0.5, which is going to be 0.5 itself. And I can write it as probability of R dash is equals to 0.5 over 0.7, which is nothing but 5 over 7. I got to know probability of R not happening, so I can take it as probability of R which is happening can be written as 2 over 7. So 5 over 7 is not happening, so 2 over 7 should be happening. Now I already know probability of S, I got to know probability of R. I can write the final answer, probability of S minus probability of R as 0.3 minus 2 over 7. 0.3 can be written as 3 over 10. 3 over 10 minus 2 over 7. I can take overall LCM as 70, which is 3 7 times 21 minus 2 10 times is going to be 20. I can write it as 1 over 70, which is nothing but option A. Now let's move to the next question. If one card is chosen at random from a neatly shuffled deck of cards, the probability of drawing a king of hearts or queen of club is. Let me explain the deck of cards here. In one deck, you're going to have 52 cards, and that deck is being divided into 4 segments. 1, 2, 3, and 4. The first one, you can call it as heart. Second one, you can call it as club. Third one, you can call it as spade. And last one, you can call it as diamond. So in which there are 2 sets of black and 2 sets of red. As of now, they're not worried about the color here in this case. And each set will have king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2, and A. We have got 13 cards, and each set will have 13, which gives a total of 52 cards. Now in this set, they have said a king of hearts, heart, and it should be a king, this one, and queen of clubs. So from the club, you're going to select a queen. So it means that you're going to have only one possibility of king of hearts, or that's nothing but plus probability of queen of club. So now if you're going to look into this, king of heart is only 1 out of a total of 52, and queen of club is again 1 over a total of 52. You can see the total answer is going to be 2 over 52, or it can also be taken as 1 over 26 as the final answer. For your clear understanding, I'm displaying the deck of cards over here. You can see we have got 4 groups: heart, club, spade, and diamond, and each set will have 13. And also you can see that 2 set will have black and 2 set will have red colors. And I hope it is clear. This is all about independent events, and let's look into the next topic, which is Bayes' theorem, in the next session. Thank you.